Right now, routing protocols are pushing packets of data across thousands of global network nodes simultaneously, calculating optimal paths in fractions of a second. Look at a modern CPU. It contains roughly 16 to 32 general-purpose hardware registers, yet the software running on it processes hundreds of active variables simultaneously. The physical silicon creates a severe bottleneck. A global internet router and a microchip share almost no physical characteristics, but computer scientists resolve the routing bottlenecks in both systems using the exact same mathematical framework, graph theory. Graph theory strips away the physical noise of a domain. It removes the silicon, the copper cables, and the geographical distances, leaving behind only two conceptual elements, vertices and edges. Once a physical system is abstracted into this pure topological state, engineers apply universal mathematical rules to calculate optimal configurations. Abstracting physical constraints into mathematical models is the strict prerequisite for scaling computational systems. Without it, routing data or allocating memory would require physical trial and error on hardware. This diagram shows the first strict topological requirement, visiting system states without redundancy. You are looking at a Hamiltonian cycle, a path that visits every vertex in a graph exactly once and returns to its starting point. The concept originates from 1857, when mathematician Sir William Rowan Hamilton posed a puzzle to find exactly this continuous cycle along a dodecahedron. But traversal is only one side of the problem. The second constraint is separating conflicting processes. In graph theory, this is modeled as vertex coloring. The rule of vertex coloring: adjacent connected vertices cannot share the same color. This limitation defines the chromatic number, the absolute minimum colors required. In production, this dictates the exact minimum hardware registers needed to run tasks without interference. Failing to correctly compute Hamiltonian loops results in infinite routing cycles. Failing to compute the chromatic number leads to severe memory spillage. These two topological properties dictate whether a system runs or crashes. In 1736, the city of Königsberg presented a geographical puzzle. Could a person walk through the city and cross its 7 bridges exactly once? Leonhard Euler solved this by ignoring the map entirely. He abstracted the land masses into vertices and the bridges into edges. In doing so, he invented graph theory. This animation illustrates his breakthrough, known as the fundamental theorem. It proves that in Eulerian circuit, a path visiting every single edge exactly once is guaranteed to exist if and only if every vertex has an even degree. Because this relies on a simple parity check, just counting whether connections are even or odd, Eulerian problems are trivial for a computer to solve. They execute in polynomial time, scaling linearly with the number of edges. Compare that to the Hamiltonian cycle we looked at earlier. A Hamiltonian problem requires visiting every vertex instead of every edge. No mathematical shortcut exists for verifying a Hamiltonian cycle across all graphs. This pushes the Hamiltonian cycle into the complexity class of NP-complete. To find an exact solution, an algorithm must systematically guess and check. As the graph grows, the required computing time scales exponentially. Shifting the target constraint from traversing edges to traversing vertices takes a problem from being instantly solvable to practically impossible to compute perfectly at scale. This exact boundary between polynomial time and NP-hard computation occurs inside modern compilers like LLVM. Their primary challenge is assigning hundreds of software variables to a strictly limited pool of 16 to 32 hardware registers. The bottleneck is simultaneous liveness. This occurs when two variables must exist in the system's active memory at the exact same millisecond. If they overlap in time, they cannot share the same physical register. Compilers translate this temporal overlap into physical geometry by building an interference graph. In this diagram, the variables are vertices. When the timeline shows two variables are active simultaneously, a solid edge connects them. The compiler's goal is to find this interference graph's chromatic number. Each available color represents a physical CPU register. No two connected variables can have the same color. Finding the perfect chromatic number for a large graph is NP-hard. There is no fast algorithm that guarantees the absolute minimum number of colors. If the compiler fails to color the graph efficiently, the CPU runs out of registers. The excess variables are spilled, dumped out of high-speed registers and written into slow main memory. This causes 10 to 100 times slowdowns in execution speed. Because compilers cannot pause for millions of years to calculate the perfect mathematical solution, they rely on high-speed approximation heuristics to find a workable, near-optimal coloring immediately. The industry standard heuristic for this is the D-Satter algorithm, short for degree of saturation. This diagram illustrates how D-Satter dynamically prioritizes which vertex to color. It ranks nodes based on how constrained they are by their neighbors. As you can see in this table, every node begins with a saturation degree of exactly 0. In step 1, because all saturation levels are 0, the algorithm defaults to the vertex with a maximum total degree, the most connected node in the graph. We assign it our first color. Now we measure saturation. A node's saturation degree is specifically defined as the number of distinct colors already assigned to its adjacent neighbors. In step 2, D-Satter recalculates the board. The uncolored nodes directly adjacent to our newly colored vertex have their saturation degree updated to 1. For step 3, the algorithm selects the uncolored node that is now the most saturated. It assigns that node the lowest available color number that doesn't trigger an adjacency conflict. This loop continues. By constantly recalculating saturation, the algorithm forces the most tightly constrained variables to be handled first, before the system runs out of registers. Heuristics like D-Satter run in polynomial time. They deliver near-optimal efficiency for NP-hard topological constraints, allowing systems to allocate memory on the fly without catastrophic delays. There are 2 critical theoretical pitfalls when applying these models in production. The first is assuming that a basic greedy coloring algorithm will naturally find the true chromatic number. Look at this bipartite graph. A greedy algorithm's efficiency is entirely dependent on vertex ordering. If we feed it a poor alphabetical order, it makes locally optimal choices without global awareness. Instead of solving it with the optimal 2 colors, it stumbles and requires 4. The second major pitfall is conflating Eulerian routing properties with Hamiltonian routing properties. Keep the boundary clear. Eulerian graphs focus purely on edges. Solving them relies on a trivial mathematical parity check. Hamiltonian graphs focus purely on vertices. They lack that parity check, trapping them permanently in the realm of intractable NP completeness. Deeply understanding this dividing line between polynomial checks and NP-hard heuristics separates a functioning architectural design from an endlessly hanging process. Graph theory acts as a universal translator. It takes physical bottlenecks, like limited silicon space or endless delivery routes, and translates them into pure topological invariance. By converting operational limits into computable vertex and edge properties, engineers bypass physical hardware constraints using algorithmic intelligence. Subscribe to Insight Engine for more high-density breakdowns of computational theory.